we're going to use more subintervals. So the last problem I did, we only did 3 rectangles, so we did 3 subintervals, but we're still doing the same thing, okay? All right, so let's go ahead and start with this, but this would be on the top of page 4. So we're just going to redo the problem, but what I've done is we're breaking it up now into 6 subintervals, which means we're going to have 6 rectangles, okay? And part of what we're doing here is to help you understand how integrals are going to work. Ultimately, in a couple of weeks here, you'll be able to get the precise answer to this problem. I'll show you how to do that like next week, just by integrating. Okay, you don't have to do rectangles, but rectangles help students understand what an integral is. So that's a part of why you're taking the time to process this like this. Okay, so what we need to do is, I'm going to just kind of have you do this. We have 6 rectangles, so and we're finding the area. So let's just say A1 and calculate it, A2 and calculate it, A3, and then let's do A4, A5, and A6. So we're basically going to find the area of each of those 6 rectangles, and then what we're going to do is we're going to add them all up, and that's going to give you an estimation of the area under the curve, and the curve is the square root of 10x from 1 to 7, okay? Now, if you find an area of a rectangle, you know it's base times height, right? You always focus on base times height. Now, I'm going to write this a little bit more mathematical because I want you to learn some symbolism. Delta x is what we use usually to represent the base, and I'll tell you what that is in just a minute, okay? And then the height is the function evaluated at whatever point you're looking at. So it's like, we usually say like x sub 1, like that. So write on here that this is f of x sub 1. And I'll explain what I mean by that, because it's basically a pretty easy geometry problem. So what I'm doing on this then is, I went ahead and just did all the midpoints for you, because we're doing midpoint rectangles. We're going to do some examples of left and right endpoints here today too. So we do that. So basically you're just telling me what the width of the rectangle is. The width of that rectangle is 1, isn't it? Because I'm subdividing. See, I'm giving you an interval 1 to 7. And if you want to find the width of the rectangle, here's what you do. You'll see me doing this over and over again. You do 7 minus 1 over 6. Okay? Subtract, find the distance between the interval I give you, which is 6, and divide by the number of subintervals I give you, so that's 1. So that's what delta 1 is. Okay, so that's going to be 1, which makes that easy. Then we're going to do f of whatever that midpoint is. Now, what's the number in the middle of 1 and 2? 0.5. It's 3/2, or we can do 1.5 if we want to. Okay, we're going to use a calculator on this thing anyway. Okay, now let's go, before we get our calculator out, let's just kind of get all these things written out, because I do want you to get confident with this symbolism. So A2 is going to be delta x, which is nothing more than the width of the base of the rectangle, and then it's going to be times f of x2. Okay, delta x is 1. It always will be. What is the midpoint between 2 and 3? 2.5. Okay, so let's just write that out, and so forth. Now, just go ahead and now just write, because you're going to see a pattern on this now. So the A3 is going to be 1 times f of what? 3.5, the midpoint, halfway between 3 and 4, right? Go to the next one. A4 is going to be 1 times f of what? Halfway between 4 and 5. A5 is going to be 1 times f of halfway between 5 and 6. And then A6 is going to be 1 times the function value of 6.5, like that. So see, you've got patterns on this thing like that, okay? All right, does that make sense? Does it make sense why I'm doing the function value? That's kind of critical. The function value is the height of the rectangle, isn't it? Because see, what you're going to do is you're going to plug 1.5 into this function, and that'll tell you how tall the rectangle is. Okay, that's what that is. Okay, so now let's use our calculator a little bit on here, and I'll show you a couple of things. I don't want that, I want my calculator. Okay, so I'll show you a couple of things that will speed you up. You don't want to get bogged down in these problems too much. I want you to use your calculator on these problems where you're crunching out an estimating area. So here's what I recommend you do. Now just follow along with me. I would go ahead and graph the thing. Don't be in polar coordinate mode. I've been teaching polar coordinates in trig. So let's see, I need to get in function mode. Okay, regular function mode. Okay, so let's go ahead and graph this thing. Got stuff in there, take it off. And what we're going to be graphing is the square root of 10x. So you want to get the 10x under there, like that. And see, by graphing this, you're going to have a lot of things that you can do at the same time. They'll speed you up. And I want you to do this. Now for the window, let's go 0 to, say, 8. Okay, I want the 1 to 7 to be in there. I want it to be a little bit bigger. Okay. All right, for the y values, if you look at my graph, I think I want to go like 0 to 10, and I think that's probably high enough if I go 0 to 10 like that. Okay, so you just want to make your x's go 0 to 8, y's go 0 to 10. Now go ahead and graph it. Okay, let's see what we got. It should look like what I gave you on the handout there. Okay. Okay, now the reason we're doing this is, hey, let's figure out what all these function values are. Because ultimately, that's all we got to do on this problem is figure out what these function values are, because the base is 1, right? So just do this. Don't waste your time. Just go trace 1.5. That will tell you the function value. Okay, let's round that off to like 2 decimals. So this thing really here is going to be 1 times 3.87, like that. Okay, and just do the same thing over and over again. Now trace at 2.5. Okay, you can do that. So that gives 1 times 5. Okay, now go to the next one. Trace at 3.5. And usually on these calculators, you only have to put trace 1 time. It depends on your calculator. So let's round this off to 5.92. Okay, go to the next one. Trace at 4.5. Okay, that looks like we're going to have 1 times 6.71. Trace at 5.5. That's going to be 1 times 7.42. And then finally trace at 6.5. And then that's going to give 1 times 8.06, like that. Okay, you guys see how I'm doing that? So if you're doing homework and stuff, and you're going to do this some on your homework when you get to this, don't waste your time. Do this. Okay? The whole thing, the whole concept is how these rectangles are working. It's not the arithmetic that I'm concerned about. Are we okay? Yeah? No? Everybody okay?
Well, so with the function that you plugged into the calculator, though, square root of 10x.
Right.
Where did you get that from?
Look at the problem. It's in the, yeah. You're kind of forgetting about the problem that we're doing. That's fine. Okay. Now here's what you do to finish this problem up. So the total area, all you're going to do is just add all these things up. Now we're going to learn about this summation notation here in a little bit today. So for now, let's just say, okay, we're doing A1 plus ... A6. Okay, take all your numbers and add them up. So we're just going to go 3.87, and if somebody will go ahead and do that for me, I would appreciate it.
36.98.
Okay, you got an answer already? Okay, good. Okay, so just add up all those areas now. Yell that answer out.
36.98.
Thank you, I could hear you. Okay, 98. Okay, very good. Okay. All right, so that's the answer. Okay. Now it's an estimated answer. Now let me ask you a question. Do you think this area is a little bit bigger than the actual area, or maybe a little less, or is it hard to tell?
A
little hard to tell, isn't it? Okay. Okay, I showed you this last time. So if you want to try this, you go second, trace. Okay, go down to option 7, which is integral of f of x dx. It's going to ask for the lower limit. What's the lower limit? 1. What's the upper limit? 7. Press enter, and it's going to draw, and it's trying to show you there's an infinite number of rectangles. Look how close we were. That's a pretty good estimate, isn't it? Okay, and the calculator's not doing calculus. It's doing what we just did, but the number of subintervals, I don't know, maybe it's 1,000 or something, because it's a computer. It can do it, instantaneously almost. That's the idea. Okay, does that make sense? Okay, so that's what we do to do that area under the curve. So that's what we call a Reimann sum. All All right, now what we're going to look at next here, I'm going to do one more thing with Reimann sums, and then I want to do a little bit with some summation notations on these things. So what I want to show you then, what I just showed you was a midpoint Reimann sum. What we're going to do is take this function, and I've already graphed this, and we're going to do left Reimann sum, and we're going to do a right Reimann sum. So what we're going to do is we're going from 1 to 5, and we're doing 4 rectangles, okay? So basically this thing that we call delta x, and delta x, you can of course see what it is on this, is the width of that rectangle. Okay, remember on the integrals when we had dx? That's technically what dx stands for, is the width of a rectangle, but it's infinitesimally small. That's what dx really means. Okay, we'll talk about that a little later here. All right, so what we do on that is we do 5 minus 1 over 4. You already know it's 1 because you can tell from my graph, but that's what you always do. You'll see me doing that over and over again. Okay, so we're going to use that in our rectangle sum thing. Okay, now left endpoints, notice what I did is I made the left endpoint of the rectangle be on the function. That's how you set up left Reimann sums as you do that. Okay. Now what we're going to do is we're just going to go ahead and crunch all this out, okay? So I'm going to write the total area. First of all, here's your rectangle number 1. Okay, now I want you to write it technically the right way here. Okay, so I want you to write delta x, that's the base. What's the height? The height is the function value of what x value? 1, because it's a left endpoint, right? Okay. The height of that rectangle is f of 1, okay? Now move on to the second rectangle, and let's write that as delta x times f of what? 2. Remember, you're on the left part here. Then go from there. You can see the pattern now. Delta x, f of 3, plus delta x times f of 4. Okay, so all we're going to do is we're going to do the same thing with the calculator to save ourselves time. So we've got 4 rectangles, so I have to do these things right there. Okay, now what's going to happen on this is one thing that you can learn to do on this, you can actually factor delta x out. I do want you to do that. Write this as delta x times f of 1 plus f of 2 plus f of 3 plus f of 4. Now we're going to go to the calculator to get the rest of this stuff. Now we said delta x was 1, so now let's go to the calculator to get the rest. Don't waste your time on the rest of this. Let's just do decimals and stuff on this then. Okay, so in working this out, put 1 over x in your calculator. The same window for the last problem probably will work out okay, so let's just kind of start it like that and see if we get a decent graph that looks kind of like what I have. Okay. All right, so we got that. Now just trace. Do this. Trace 1. Okay, you get 1. Okay, so f of 1 is 1. Trace it 2. That's 0.5 or a half. Trace it 3. That is a third. It's really 0.3 with repeating 3's. Trace it 4. That's going to be 2.5. Okay, then we can take our calculator and add them all up. Oh, is that point? That's 0.25. Sorry. Yeah, makes sense. It's getting smaller. Okay, now just add it all up on your calculator. And the way I would do this is like this. I just do 1 plus 0.5 plus, I'll put a bunch of 3's in there because I know it's repeating 3's, plus 0.25, like that. Then that gives that for you. So you can do 2 things on this too that's kind of cool with technology. You can write that as 2.083, or you can do this. You have a math button. You can press your math button and convert it to a fraction. Okay, it didn't work. Sometimes it works, sometimes it doesn't work. It's because I didn't put enough 3's in.
It's 25 12s.
So what did you end up getting on that?
25 over 12.
25 over 12? Okay.
Yeah.
And let's see, 25 over 12 was, yeah, okay. So that the exact answer, I was going to try to show you the calculator to do that. is 25 over 12. So that is the left Reimann sum, which gives that, okay? All right, now if I do this thing on the calculator, if I do the graphing like I did, and again, if I go second trace, option 7, the lower limit on this, we're integrating from 1 to 5. So we go 1 to 5. This should, now that's, oh, hold on, that's doing the exact area under the curve. So notice this is an overestimate. And does that make sense from my diagram that it's overestimating the area under the curve? Okay, that's what happens because of the way the function goes. Okay, now let's go ahead and do the right Reimann sum. Now you can save yourself a little bit of time by doing a couple of things. When we do the area total, it's really going to be delta x times the sum of all of those function values. Okay, you can factor that out. Now this time, when you look at the first triangle, what are you going to use? F of 1 or F of 2 to give the height? F of 2. Okay, that's what you're looking at. That's how tall the rectangle is. Okay, you got to go to that function value to do that. So you're going to do F of 2, then you see the pattern. Then you're going to go F of 3 plus F of 4 plus F of 5 like that. Okay, then you've got your right endpoints. Okay, then again, we can just do the same thing. We can get all that stuff calculated out. I think we already had F of 2 was 0.5 from the last problem. F of 3 was really like a third. It's 0.3, so that was a third. F of 4 was 0.25, so that's really a fourth. Then I need to just trace at F of 5. Okay, so if I trace at 5, that's going to give, I can't even see that. What does that say?
0.2.
You can also go like this. You can go second graph to get your table to come out. So if you look at F of 5, it's going to give 0.2. You can look them up in a table that way too sometimes, and that's faster. Okay. All right, so that's 0.2. Now just add it up, because what delta x was 1, then we can add all those values up and get an answer. Anybody do that yet?
1.28.
1.28.
77/60.
Okay, you got 77/60. Very good. Okay. All right, because it's just adding that up on the calculator, and you'd have that. And again, this one underestimates. Okay, so, and again, what you're doing on this is, you know, you can go 0.5 plus a third. If you put a third in, it'll probably work. And then plus a fourth. You see a pattern on this too. Okay, and then plus 0.2. You can add all that up. Then if you go math fraction, then it takes it to 77/60. So that comes in handy. That math fraction button will convert decimals to fractions for you. Okay, you can do it by hand too with getting fractions and stuff like that if you want to. Okay, all right. So you guys got any question about that? Yeah.
So what answer should we give, the decimal or the fraction?
Either one. If I ask for an exact answer, you give the fraction answer. If I ask for an approximated answer, then you use a decimal. Okay. Okay, let's go to the next thing. I do want to work out a few more things before we do a break here. So I want to do a couple of things just a little differently here. This one I'm going to do, now I'm not going to do both. I'm going to just do maybe a left endpoint and a right endpoint on one of them. So mainly what I want to do is I want to do the area under the curve of the cosine x from 0 to pi over 2 using 4 rectangles. And this time I'm just going to say let's do a right endpoint. Okay, I'm not going to do both. That's kind of time consuming. Then on the next problem maybe I'll do a left. I've already done a midpoint, so we want to do that. Okay, so to begin with, you want to go ahead and find that delta x, which is the width of a rectangle. Okay, sometimes you can do it in your head. So what do? I've been doing this over and over again. You do the distance between the end of the interval to the beginning of the interval, then you divide by how many rectangles I want you to do. So that's going to give really pi over 2 divided by 4. That's pi over 2 times a fourth, so that's going to be pi over 8. So that's going to be the base of that triangle. And you have to be in radians, okay? Or you can't have a base of a triangle in degrees, right? That doesn't make any sense. Radians is a real number, okay? So we're going to go ahead and we're going to draw a graph on this then, okay? So let's just kind of get us a graph put together when we do this then. All right, now what we're going to do is we're going to count off by pi over 8. Okay, if you took trig, I mean, you do this a lot. Just pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. Okay, that's how we're going to divide these subintervals, because we're going to divide them by pi over 8s. Okay, so let's go ahead and put that on here, but use reduced fractions. So this is pi over 8. 2 pi over 8 is really pi over 4. 3 pi over 8, you do that. And then 4 pi over 8 is really pi over 2. So see, all I'm doing is I'm taking the interval I gave you, but I'm breaking it up into 4 rectangles. That's why I came out with pi over 8. Does that make sense? Okay. Now, we're going to graph this. Hopefully you guys don't need your calculator to graph a basic cosine. Okay, it's going to go up to 1. What's the first point on a basic cosine? 0, 1. How about pi over 2? That's 90 degrees. The point 0, 1, that goes to 0. All we're doing is we're doing a slice of the cosine, like that. All right? And we're going to estimate the area under the curve from 0 to pi over 2 using right endpoints this time. Okay? All right, so here's what you do. Watch this carefully. When you go to pi over 8, since we're using a right endpoint, you want the rectangle to be measured from that point like that. And then you can kind of just sketch in your rectangle like that. Okay? Go to pi over 4, go up to the function. That's how high the rectangle is going to be. The right endpoint of the rectangle measures the height. Go to 3 pi over 8, do it like this. Now what do you think's happening at pi over 2 if I do a right endpoint? I have kind of a real flat rectangle, right? With 0 area, right? Okay, I mean, that is a rectangle. It's just got 0 area, okay, because the function value that you're really going to be doing is pi over 2, like that. So what you have is we're going to find the area of these 4 rectangles. Of course, we know the last one's going to be 0, like that. All right, so what you want to do on this then is show your work like this. You can just say that the total area is equal to delta x, which we found. And see, delta x is always the same, so it's factored out. Then you're going to do f of, now help me out, what are you going to use for this first rectangle? F of what? Are you going to use 0 or pi over 8? Pi over 8, because it's a right rectangle. Okay, go to the next rectangle. What are you going to use? Pi over 4. See, that's what I mean. Okay, like that. And then we go to 3 pi over 8. We're going to go f of 3 pi over 8. And then f of pi over 2, like that. Okay? Now again, we'll use calculator sum on this. Some of this stuff you would have to actually get into your calculator on some of this. So anyway, what was delta x? It was pi over 8. Okay. Now, a good thing to do, again, when you're doing these problems, I just recommend, in the modern age, that you use technology as much as you can to assist you, and you can kind of check the answer almost at the same time. So what you want to do is you want to go ahead and put in cosine x. If you want to do this along with me, you can. Then we're going to do a window. Let's do, we're going to 0 to pi over 2. So we just go ahead, you want to make sure your calculator's in radian mode. We do that. We divided and scaled this up into pi over 8, so I can scale it by pi over 8 if I want to, which is what I'm going to do. And then the y's, we're going to go 0 to 1, okay, like that if you want to do that like that. And then you should have a good graph, making sure that you're in radian mode on that then, okay? So I'm going to 0 to pi over 2, scale by pi over 8, and then 0 to 1 on the y-axis, okay? And you should get, hopefully, what I just graphed, okay, like that, okay? So what we're going to do then is we're just going to find each one of these things. Some of them go from the unit circle, some don't. But if you just trace at pi over 8, you just go trace and then put pi over 8, okay? That'll give a bunch of decimals. Let's just round to 2 decimals, so let's say 0.92. Do you guys remember what the cosine of pi over 4 is? Square root of 2 over 2, okay. I'll put that on there, too, but we'll end up rounding it anyway, okay. All right, then we're going to go 3 pi over 8, which is going to be 0.38. And then how about the cosine of pi over 2? We said that's 0, right? Okay, right? No. Okay, so pi over 2 cosine 0. Then what we can do on this is we can just do the rest of this on the calculator. So I can just go pi over 8 in parentheses, and then 0.92 plus, and then you can go ahead and put square root of 2 over 2. You could have gone ahead and used a decimal on that if you wanted to. And then plus 0.38, and then plus 0, which you don't have to do, of course. Okay, so anyway, you would get an answer of approximately 0.78, like that, and that's probably good. Now let's just round that to like 0.79, and that would be an approximate area. Okay. Then if you wanted to check and see how close you are, you could go second trace, do the option 5, and what you're doing, whoops, I did the wrong thing. So you could go option 7, lower limit 0, upper limit was pi over 2. Okay, and then this will tell you a pretty close estimate, and a lot closer than ours. So we'll see how close we are. Okay, 1. Interesting. That's the way the math works out. If you used exact numbers on that, that's the way it goes. But the thing is, once we learn how to do what's called the fundamental theorem of calculus, we'll be able to get that answer. We don't have to do rectangles anymore. The rectangle idea is preparing you to help you understand the fundamental theorem of calculus. That's the idea. Okay. All right. Well, let's go ahead and do our. All right. So I'm gonna do one more. This time I'm gonna do a left endpoint. Okay, and then this is probably enough. These things get tedious, but like I say, it's just kind of getting the idea. This one's not bad because it's 4 rectangles and on a pretty short interval on this. Okay. So the first thing you want to know how to do is find delta x. How do you do that? The distance between the interval I give you, which is subtracting, and then divide by the number of rectangles. So this time it's 2 over 4, or 1/2. Okay? So if you're going to scale this and everything, what you really do is you just count by 1/2. So you're just going to, when we put this together, we're going to count by 1/2. So let's go ahead and construct a graph on here then real quick and get a good picture of how this graph goes. Okay, now there's a few things on this that we want to go ahead and do. We're going to go from 2 to 4. So mainly I'm just going to kind of go over here to 2 and then over to 4. We'll have a 3, and then you'll have your subintervals like that. So you're just going to have 2, 2.5, 3, 3.5, and 4 like that. Okay. Now, as far as graphing goes on this, there are a few things that you can do. You know, all you got to do is just get it's a parabola, right? So without touching my calculator, I don't want to get too reliant on the calculator. If I plug 2 in, I'm just going to have 2 squared minus 1 is going to be 3. So that means that we have a y value there of 3, which is pretty important in the problem. Okay. Then if we go to 4, I'm just going to go to the next one at 4. I think I'll just go ahead and do all of these. So if I do 3 to the second minus 1, then that's going to be 9 minus 1, so that's going to be 8. So let's just take that up and see, just label it like 3, 8. You don't have to make this accurate because you're going to be estimating the area anyway. So that's 2, 3, that's 3, 8. Then if I do 4 squared minus 1, that's going to be 15. So just kind of do something like that. Okay, you know it's a parabola. That's not a very accurate one, but you get the idea, right? Okay. Now, this time I said let's do left endpoints. I want you to be able to do all of those. So we're going to do 4 rectangles. You always start with, what's on the left. So you're going to have your rectangle is going to go like this. That's going to be your first rectangle. You got 4 rectangles. The second one, again, is going to go like this. The height is defined by the left rectangle, or the left endpoint. So it's going to go like that. Okay, and then the next one is going to go kind of like this. You're just trying to get kind of a good idea of what's going on. Okay, you guys got the left and right endpoint down okay? The midpoint just means the midpoint would define how high the rectangle is, okay? So now we're going to find, we got 4 areas, A1, A2, A3, A4. So we're going to do the total. So when we do the total of the area, that's going to be delta x times, and see, delta x is always going to be a half on this problem. The distance on all these bases of the rectangle is a half. Okay, that's what we did over there. So now we just need to do our function value. So if we do, for the first rectangle, what are you going to do? F of what? 2. Good. For the second rectangle, what are you going to do? F of 2.5, right? Okay, for the third rectangle, what are you going to do? F of 3. And then for the fourth rectangle, you're going to do F of 3.5. So we're going by halves, like that. Okay, does that look good? Okay, now let's just keep doing what we've been doing, mostly kind of using technology on this. Okay, so let's put in the function x squared minus 1. Okay, let's make the window go, let's go 0 to 5. That way we'll have a good picture of what's going on. And let's go 0 to 20 on the y-axis, okay, because we have that point 415 on that. Graph it, you'll have your parabola. And remember, we're only going from 2 to 4 like this, okay? So what you can do again is just trace, okay? Trace it 2. That's 3, okay? Delta x, we said that delta x was a half. Now f of 2 is going to be 3. Trace it 2.5. That's going to be 5.25. Okay, trace it 3. That's going to be 8. Trace it 3.5. That's going to be 11.25. Now you can do this with exact numbers with fractions if you want to. I just don't want to take the time to do that. So now what we could do is 1/2 is 0.5. So I'm just going to go 0.5 and then times the sum of all these function values. And let's see what we get there. Okay, so we get a total area of 13.75, which is actually 13 3/4, right? So that would be the exact answer like that if you did that, okay? And then again, you could check your answer on this one. You can tell that it underestimates on this one because all the rectangles are below the curve, so you could also do what we did on the graphing calculator. Go to option 7, lower limit on this problem's 2, upper limit's 4. Do that, that's what we just found. So we're underestimating a little bit, aren't we? Okay. All right, now that's going to be the end of my Reimann sums. Okay. All right, but you get the idea. The idea I'm trying to generate here is the more rectangles we use, the more accurate the area becomes. And calculus will allow us to make the width of the rectangle infinitesimally small. So in other words, we'll be able to sum up an infinite number of rectangles and get a finite area. That's weird, isn't it? That's real weird. That's the way it works. All right, so next thing I want to do, just finish this up, is I want to look a little bit at some summation notation and just kind of show some of this. You may or may not be familiar with this. You use this primarily to help you make a relationship between an integral and an infinite sum of numbers, okay, like this. So first of all, what I want to do, I'm going to kind of do this backwards. I'm going to go over these rules in just a minute. But let's go to the page that has this number 41. I took this out of the book. And I'm going to show you what these problems mean. Then I'll kind of backtrack. It's easier to learn it this way before you learn it the other way. Okay? So one thing that you want to get comfortable with is what this means. This, if you haven't seen that before, that just means a sum of numbers. It's summing. You're going to find the integral is also going to mean a sum. But it's going to mean a sum of an infinite number of rectangles. Like that. That's the difference. This is a finite number like this. All right. Well, if you had this problem, here's what this problem means. This is where you start. That's a counter. That's where you start. That's where you end. So what you would be doing is, if k is equal to 1, you just plug it in, so you get 1. Okay, this counter is going to change, and the counter always changes by whole numbers. So now it's going to go to 2. So you're going to go 2 like that. Then you're going to go, the counter now goes to 3. Then it goes to 4, 5, 6, 7, 8, 9, and then it stops at 10. So that's an abbreviation for that sequence of numbers. K is changing from 1 to 10. Okay, then you could add that up and you could get the answer. Okay, all right, I already know the answer. I'll let somebody do that and tell me what the answer is if you want to. All right, there's a formula that applies for that too that we'll talk about here in a minute. So anybody get an answer? Anybody do that?
55.
55, okay. Okay, so the key thing is to understand the notation. That's what I'm trying to learn, okay? All right, now the next one, we're going to do this. Okay, we're going to start by doing 2 times k plus 1. And I'm not going to sum all these things up. The idea mostly is to see what this thing is doing. So what do I start with first? I start with 1. Okay, then I just do the same thing over and over again. So I've got 2 times k plus 1. Over and over again. Until you get to 6. Well, this is mainly what I want you to write out on this. And then some of these things have formulas, and we'll talk about that a little bit here. So basically, we're just going, the k is going from 1 all the way up to 6. So then we'd have 2 times 5 plus 1, and then finally we would have 2 times 6 plus 1, like that. Okay, I'm not going to sum it up. We'll do that later. Okay, so that's the meaning of that problem. Okay, does that make sense to everybody? K starts at a number and it just goes up by whole numbers. Okay, these things are called sequences. You'll learn a lot about this in calculus too. Okay, so the idea with this next one is, okay, you're just going to do something squared over and over again, and then you're going to sum those things up. You're always summing these things. So what you're doing is the counter is going 1, 2, 3, 4. There's a formula for the sum of squares, 2, that mathematicians have figured out. Okay, that's a little bit earlier in the handout. I'll talk about what some of those formulas are. Okay, and then the next one is going to be, it's just 1 plus 1 squared plus 1 plus 2 squared plus 1 plus 3 squared, plus 1 plus 4 squared, plus 1 plus 5 squared. Okay, if you were going to add that up, you could use your calculator to help you. That's not what I'm concerned about as much as I am that you understand what that, we call that sigma. You might write a note down on that because I call this a lot of times a sigma sum. Have any of you ever taken statistics? You see that sigma thing all over the place in statistics, don't you? Because you do a lot of sums and stuff, okay? Okay, everybody got that okay? All right. Now let's back up. Now let's do it backwards. Then I'll go back to what I just did a little bit, on some of them. Okay, now the other thing is, okay, you want to be able to do this backwards also. It's usually a little harder for students to do this backwards. So number one, we're going to write our sigma sum. This is really where we're starting. That's where the counter starts. That's where the counter ends. And that counter is always going to go up by 1. Okay, that's how these sequences work like this. So we would just pick a variable. K is pretty typical. We're going to go K equals 1 to 5. And then what do we put there? We put K. Because it's K that's changing, right? Okay, it's going to be just 1 plus 2 plus 3 plus 4 plus 5. So that's how you take that and do that in reverse. Does that make any sense? Okay. You can tell you're right, too. I mean, you can work it out and make sure you've got everything right there. Okay. And I'm not giving you anything very complicated. We're going to keep this pretty straightforward. Okay, so the next one. Where does K start? Where does it end? Okay, so that's how you get that. What are you doing? You're just adding those numbers, so you just put K there again. Okay, because all that's going to indicate is 4 plus 5 plus 6 plus 7 plus 8 plus 9. All of these plus signs, that's what the sigma thing is doing for you. Okay? All right, let's see if we can do the next one. Where do I start? Where? 1. Where do I end?
4.
What do you think goes here?
K squared.
Good, k squared. That's it. Because you're just squaring whatever that k is. Okay? And then D, we would have sigma sum, and we're going to start from, and one thing that might help you a little bit, this is a 1 over 1. So what is the numerator always going to be? Well, you got to have that. You have to have a 1 there. It's not going to change. It's the denominator that's changing, right? So you're going to put 1 over k there. Then you're going to go from 1 to 4. So you say k equals 1 to 4 like that. Now, I don't give anything very complicated, okay? That's not the point behind this. Part of the point in this class in calculus is to understand we can express Riemann sums with summation notation. And then ultimately that turns into an integral, which is what we're going to be working on the rest of the semester, okay? Now, the only thing else that I wanted to do is I wanted to just kind of look at some of these formulas right here. So we have a formula if you're just doing the summation of k. It's n times n plus 1 over 2. We have a formula for the summation of k squared. And then we have summation for cubes and all kinds of things like that. Okay? Let's see. One of the people that's considered to be one of the greatest mathematicians of all time is Gauss. I mean, he's like at least top 3. But a lot of people say he's the king. I'd say he's the king. And the legend is when he was in 4th grade or something, the teacher gave him this problem. They said, I want you to add all of these numbers up. I guess she was just giving them something to keep them busy. So the kids, they were just working away and adding those numbers. And Gauss, in about a minute, had it figured out. He figured out that formula when he was like in 4th grade. So it's kind of an interesting story. So what you would really do on the problem, this is what Gauss did, is we're doing the summation of the numbers from 1 to 100. Really what you do is you just take 100, and then that's n plus 1, 101 over 2. That becomes 50, so you just do 50 times 101, you got the answer. That's a pretty smart kid, isn't it? That's the legend anyway. Okay, he figured that out. So all these problems that we did before, I'm not going to go through all these, but this problem right here, you can write down this if you want to on this. If you did this problem now, here's what you do. You take that top number 10, multiply it by 11, and then divide by 2. Okay, like that. So if you do that, that's 5 times 11, that's 55. I think somebody did this for me and said 55, didn't they? Okay, so if you do a summation of k, it's just k times k plus 1 over 2. That's how that works out, okay? Now the k squared goes, some of these I forget, the k squared is n times n plus 1. Let's write that down. N times n plus 1, then I think it's 2n plus 1. You guys don't have to know these formulas. 2n plus 1. Now, what was that over? I bad short-term memory problem here, 6. Okay. All right, so what you do in this problem to get the answer is you would just take the top number 4. You would take 4 times 4 plus 1 or 5. Then you do 2 times 4 is 8, plus 1 is 9, over 6. Then you could work that out, okay, from there. That's how you do it, okay? So that would give you the sum of the squares on that problem if you did that. So that's really going to be, I think, 180 over 6, so it's 30. So if you did that and took the time to do that out the long way, you'd get 30, okay? Isn't that cool? Well, somebody's got to figure all this stuff out. There's methodology to figuring that out. But, that's what mathematicians do. They always look for an easier way to do something, okay? Okay, wouldn't you get sick of doing Riemann sums over and over again? I'm already sick of it. I want to teach you how to integrate so we can get those answers fast and efficiently and exact. That's the idea, okay? Okay, so that'll kind of wrap us up with that.